question of everything.
We'll begin this lecture with the same setup from the last video of the last lecture. The big idea in this lecture is we want to understand how to think about linear transformations between two vector spaces in terms of matrices. And for this lecture, we're going to very closely follow section 11.2 of Dummett and Foote, the matrix of a linear transformation. So here's the setup. Let V and W be vector spaces over F. Let B be the set of vectors V1, V2 up to Vn, be an ordered basis for V. And E be the set of vectors W1, W2 up to Wm, be an ordered basis for W. Phi is going to be an element of Hom F VW, an F linear homomorphism from V to W, or an F module homomorphism. But what does that really mean? It's just a linear transformation from V to W. We want to take this linear transformation and express it in terms of a matrix. So what we'll do is for each j from 1 up to n, we're going to write phi of vj as a linear combination of these wi vectors. So we're going to write it as a sum from I equals 1 to m of alpha ij times wi. So these alpha i's are elements of our field F. So what question is this answering? Where does phi send each element of our basis B? Well, it sends it to some vector in W. So how are we answering this question? We're taking that vector in W and expressing it in terms of this basis E. So you can write any vector in W as a linear combination of these basis vectors in E in a unique way. And that is the answer that we're getting here. We're saying phi sends our basis element to some vector in W, and we're expressing it as a linear combination of the vectors in this chosen basis E. We'll define M, B, E, phi to be the m by n matrix whose ij entry is the alpha ij that shows up here. So how to think about this matrix? Well, if you fix j to be 1, these are all the alpha I1s. Where do they go? They go into the first column. So the first column of this matrix says where phi sends the first element of the basis B of our vector space V. So the first column tells you where V1 gets sent. What do I mean tells you? It gives you the coefficients of the F linear combination of the basis vectors of E that tell you where the first vector V1 gets sent. The second column says where phi sends V2, where phi sends V2 as a linear combination of the elements of the basis E for W. Third column says where phi sends V3, and so on. So this matrix is special and gets a name. This is called the matrix of phi with respect to the bases B and E. All right, so what are we seeing? If you make a choice of basis for V and a choice of basis for W, then for any linear transformation phi, you get an m by n matrix with entries in F. So this matrix, the columns are telling you where phi sends the basis vectors. But since every element in V is a linear combination of these basis vectors of B, if you have this matrix, you know where phi sends any element of the vector space V. So I'll pause and erase, and then I'll write that down more carefully. And soon we'll move on to looking at some explicit examples. If we know this matrix, what do we know about the linear transformation phi? I claim that the answer, in some sense, is everything. Given MBE phi, we can recover phi. What do I mean recover phi? I mean, we can say where phi sends any vector V in the vector space. That is, MBE phi tells us where phi sends any little v in V. So how do you start with this matrix and see where phi sends little v, we start by writing this vector in terms of the basis b. So we write it as a sum from I equals 1 to n of gamma I times vi, where these gamma i's are field elements. We know that our vector is a linear combination of our n chosen basis vectors with coefficients in f in a unique way. And then we calculate the product of this matrix MBE phi times this column vector, whose coordinates are these coefficients when we write v as a linear combination of the basis vectors of b. The output is some column vector of length m. So where does phi send v? Well, that just is phi of this linear combination. But phi is an f module homomorphism. So that's the same as phi, or the sum from I equals 1 to n of phi of gamma I times vi. But then you can pull out the scalars and write this as a sum from I equals 1 to n of gamma I times phi of vi. And then what is that? Well, each phi of vi is expressed as a linear combination of elements of the basis E as the ith column of this matrix, MBE phi. And how do you multiply an m by n matrix by a column vector with n entries? Well, you just take gamma 1 times the first column plus gamma 2 times the second column plus gamma 3 times the third column, and so on. So this expression here is the product on the right side expressed as a linear combination of elements of the basis E. So what's going on here is that the equality here is saying that the product of these matrices, this is how you multiply an m by n matrix by a column vector of length n. Okay, so what does all of this mean? Is that the column vector of coordinates of phi of v with respect to the basis E, that is, these are the coefficients in f when you express phi of v as a linear combination of elements of this basis E. Where do these come from? They come from taking this matrix and multiplying it by the column vector of coordinates of v when you express it as a linear combination of the basis, this should say of the basis b. So the coordinates of phi of v with respect to the basis E come from taking this matrix and multiplying it by the column vector of coordinates of v with respect to the basis b. The starting point is you write v as a linear combination of elements of your basis b. So this is sometimes expressed with this notation, which I'll be honest, I don't particularly like, so I probably won't use it again, but you should be familiar with it in case you see it somewhere else, that you take this vector phi of v and you express it in terms of this basis E. So that's saying that phi of v, you think of it as a linear combination of these basis vectors E, and you write down a vector whose coordinates are the elements of f giving that linear combination. That's equal to this m by n matrix times the same thing over on this side. You have this vector v. You can write it as a linear combination of the basis vectors in B. And then you write down a vector whose entries are the elements of f giving that linear combination. So I'll pause and erase, and we'll go on with some additional definitions and then some examples. This m by n matrix, MBE phi, associated to this linear transformation phi, is said to represent the linear transformation phi with respect to the bases b and e. So we have this matrix that's associated to phi, and it depends on a choice of bases b and e. And we say that this matrix represents the linear transformation phi with respect to the bases b and e. Similarly, if you have a linear transformation, there's this corresponding matrix once you make a choice of bases b and e, and phi is said to be the linear transformation represented by this matrix with respect to the bases b and e. So one big question to keep in mind is you can fix a linear transformation and vary over all of the different choices of bases and ask, what different sets of matrices do you get? So one way to ask that question is, when do two matrices represent the same linear transformation phi, but with respect to different bases? And this is something that is the subject of part of the end of section 11.2, not the very end, but right before that. And this is where we'll start the next lecture. So this is just a question that I would like you to keep in mind as you first start thinking about how linear transformations and matrices relate to each other. So I'm going to pause and erase, and we'll look at some examples. Let's look at a first easy example. Let's say v equals R4 with the standard basis vectors for b. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And let's call these E1, E2, E3, E4. Let's take w to be R2 with the standard basis 1, 0, 0, 1. So we take a linear transformation phi. It should send an element of R4 to an element of R2. Let's take the example phi, which sends w, x, y, z to x plus 2y plus 3z, w minus z. I picked this example kind of randomly. It's a lot like the first example given in dominant foot, but it's not exactly the same. So here you at least get a slightly different one. So we want to write down the matrix of this linear transformation, the matrix representing this linear transformation with respect to the bases b and e. So the columns of the matrix are going to come from where phi sends the elements of our basis b. So let's just write that down. So phi of the first basis vector is 0, 1. And phi of the second basis vector, we put in 1 for x, 0 everywhere else, is 1, 0. Phi of the third one, 1 for y, 0 everywhere else, 2, 0. And the last one gets sent to 3 minus 1. So what is the matrix of this linear transformation? Well, we see, for example, that the first column is 0, 1 because this vector is 0 times the first basis vector in E plus 1 times this second basis vector in E. The second column of this matrix is 1, 0 because the second, where does phi of the second basis vector here get sent? E2 gets sent to 1 times the first basis vector in E plus 0 times the next basis vector in E. And so on. So each column is keeping track of the coefficients in F, in this case, in the real numbers, that give us the phi of EI as a linear combination of the basis vectors in E. So once you have this matrix, where does phi send some vector in the original R4? Well, you write it as a linear combination of your 4 standard basis vectors. So let's say a sum from I equals 1 to 4 of VI times EI, where now our VI are in our field F, which for emphasis, I will say these are going to be our real numbers. So phi of V is this 2 by 4 matrix times this column vector of length 4, keeping track of the real numbers that give V as a linear combination of the 4 standard basis vectors. And we just take V1 times the first column plus V2 times the second column. You can take those scalars and put them into those column vectors. And we see that in the end, what do we get? We get phi of V gets sent to the vector V2 plus 2V3 plus 3V4, and then V1 minus V4. Or if you like, you can think of it as this real number times the first standard basis vector of E times plus this second real number times the second standard basis vector in E. OK, so this process is very mechanical. You can write everything down and fill in all of the entries of your matrix, and then you'll be able to see where your linear transformation sends any vector in your original vector space V. So I'll pause and erase and go through one additional example. The next example I want to give does come directly from dominant foot, and I want to keep this example because we're going to come back to it in the next lecture. Let's say V is equal to W is Q cubed, Q to the third. So it's going to be vector space over Q, and V and W will be the same vector space over Q. And we'll pick the same basis for each. We'll pick the 3 standard basis vectors, 1, 0, 0, 0, 1, 0, 0, 0, 1. Suppose we have a linear transformation from V to W, but W is V, so V to itself, defined by V sends XYZ to whatever this is, 9x plus 4y plus 5z minus 4x minus 3z and minus 6x minus 4y minus 2z. We want to write down a matrix that represents this linear transformation with respect to the bases B and E. So we have to see, where does phi send each of our 3 standard basis vectors? Well, it sends the first one to 9 minus 4 minus 6, by which I really mean that's the vector it sends it to. And expressed as a linear combination of the standard basis vectors, it's 9e1 plus negative 4e2 plus negative 6e3. Where does it send the second standard basis vector? 4, 0, minus 4. The third, 5, minus 3, minus 2. And now we can just write down the matrix representing phi with respect to these bases B and E. It is MBE phi. The first column is 9 minus 4 minus 6. Second column, 4, 0, minus 4. Third column, 5, minus 3, minus 2. Because what is this first column? It's answering the question, where does phi send E1? It sends E1 to 9E1 plus minus 4E2 plus minus 6 times E3. Second column, same thing. Where does phi send E2? Third column, where does phi send E3? So these computations, there's stuff to write down, but everything is very mechanical and straightforward and should be familiar to you from when you first learned linear algebra.